Okay, thank you everyone. Good morning, good afternoon, good evening. How are you doing? Hope you're doing great. Welcome to our course on thermodynamics. So we'll be continuing on what we started last time on thermodynamics. Last time we defined the concept of thermodynamics as the relationship between heat and work. And we were able to show some key application areas of thermodynamics. And there are two broad categories of the applications of thermodynamics. Number one, in heat engines, where we convert heat to mechanical motion or work, which is applicable in cars that we drive, in some of the machineries that are powered by engines, and of course, in electricity generation. So conversion of heat to work. And the technical term for the equipment or the device that converts heat to work is what we call heat engines. Heat engines, the engine in your car, the steam turbines, gas turbines, and so on. These are various applications of uh, heat engines and the broad areas in which they are used in vehicle motion, machinery motion, and in power generation. By power generation, I mean electric power generation. And we said that heat is actually energy in motion from one point to another due to temperature difference. And that energy in motion is actually microscopic because more often than not, we're not going to see a physical displacement of the body due to the motion of the heat. The heat is moving, but we are not seeing with our eye how the heat is moving. However, in the case of work will involve mechanical motion. It could be linear motion, it could be rotational motion, but there's mechanical motion. And mechanical motion is when force is applied to a body and the body moves a distance, or the points in the body move a distance in the direction of the force. And we're able to show, basically in fundamental terms, how heat engines work. So today we're going to be continuing on heat engines. And at this point, let's share our screen. So we're going to be beginning with a question. And the question is this: mathematically speaking, what is work in thermodynamics? Yes, we already know that work is mechanical motion. Yes, but in mathematical terms, or if you want to do some calculations, how do you calculate work? And what is work? What variables are important in the calculation of work? So I put in 5 different options. Option 1 or option A is force times distance. Option B, pressure times volume. Option C, torque times angular displacement. Option D, the integral of variable 1 over variable 2 in each of the above. That is, for instance, integral of force over distance, or integral of pressure over volume, or integral of torque over angular displacement, any of them. And when we say integral, of course, you know what integrals are, isn't it? That's integration, mathematical integration, which is a subset of calculus. So these are the options. So can you hazard a guess as to the correct answer? Type your answer in the comment section now, and let's see as we go ahead which of the answers is correct. Okay, let's now go to slideshow mode. Now let's look at the relationship between force and distance. In general, work in physics is usually defined as force times distance, isn't it? Force times distance. Now, when the force is constant, now if you try to visualize the situation in a graph, a graphical plane showing a plot of force applied to the body or to the point in the body against distance moved by the body or the point in the body, we see that if force is constant, a constant force F is applied over a distance, we can represent the relationship by a horizontal line parallel to the x-axis because force is constant. And then the work, we generally define work in this case as force times distance. And many people do not really know that this equation, force times distance, only applies when the force is constant. If the force is not constant, then this equation, force times distance, will not apply. Now, there's a general relationship. The general relationship between work, force, and distance is given by the integral of the force as a function of distance over the distance. So this is a general behavior. Now, this W equals Fx is a particular case of this general behavior. Now, in general, the work done by a force through a force F through a distance x is given by the area under the force against distance graph. The area under the force distance graph. And this is what applies here, what we have quoted here, which is the general form, regardless of the nature of the force, whether the force is constant or it is varying. This is the equation that tells you the work done by the force. So how do we move from here to here for a constant force? For those of us familiar with the laws of integration, we know that if F is constant, F can come outside the integral sign, and so we'll now have W equals to F integral dx. It will now be F integral dx. And integral of dx from 0 to x becomes x. Basically, work will now be F times x, and we arrive here. So this equation is a particular case of the general equation where F does not depend on x, but is a constant. So in general, work done is the area under the force distance graph. Now, let's go beyond force and distance. And let's go to something that's more practical when it comes to the behavior of gases. Remember, we say work is done in heat engines by controlled expansion of gases. So, Recall that pressure is an important variable for the behavior of gases, isn't it? Of course, yes. And pressure is force per unit area, which means force is equal to pressure times area. So if we replace the general equation for work from the previous slide, where we say work is the integral x0 of f dx, if we replace that f with PA, now where P is pressure and A is area, this is what we have. Remember, in a practical system, the force applied, like here in a piston, as you see in the reciprocating piston here, the force applied is applied over a cross-sectional area, in this case, the area of this circle. So when the piston moves through the gas and compressing the gas or expanding, when the piston moves like this, it moves through a cross-sectional area. And that cross-sectional area multiplied by the displacement dx will give you the change in volume. So A dx is equal to dV. That is change in volume. So if you replace this A dx by dV, in which case every term in x changes to V, then we have this equation transforming to this equation. And so work now becomes the integral of pressure over volume. So we see the translation from F dx to P dV. And so, by the laws of integration, as we have explained earlier, if P is a constant, if we have what we call an isobaric process, a process at constant pressure, then P can go outside the integral, and we now have W equal to P integral dV. And integral dV from 0 to V is V. And so we arrive at this. For constant pressure, work is equal to PV, or change in V. Now, when you move from 0 to V, if you move from, let's say, V1 to V2, it becomes V2 minus V1. So work will now be P bracket V2 minus V1. So that's the work done. So we see that work done is now expressed in terms of the pressure of the gas and the volume of the gas. So this is the practical form in which work is described generally for gases, because gases have volume, gases have pressure. So pressure and volume are practical variables in thermodynamics as against force and distance, or force and displacement, which is more common in engineering mechanics. Now, let's go a step further. You see, in thermodynamics, linear motion of the piston ultimately results in rotational motion. And when we are talking of rotational motion, we move from linear force F to rotational torque T. So T is basically, torque is basically the turning effect. It's basically related to turning moments, isn't it? Yeah. So now, torque, when rotational motion happens, then instead of having linear displacement x, we have angular displacement theta. So angular displacement theta replaces linear displacement x. And in the same vein, torque T in Newton meters replaces force F in newtons. Now, torque T is given by I multiplied by alpha, where I is moment of inertia and alpha equals to d squared theta over dt square is angular acceleration. Now, does this equation sound familiar? Have we seen this kind of equation, a parallel to this equation before in the linear motion space? Think very well. Yes, Newton's law of motion. Newton's second law of motion, which says F is equal to ma. That is force, linear force, equal to mass times acceleration. Mass times linear acceleration. So that applies to linear motion. For rotational motion, you replace the force with torque. Linear displacement is now angular displacement. Mass for linear motion become moment of inertia for angular motion, while linear acceleration is replaced with angular acceleration. So moment of inertia depends not only on the mass of a body, but on the distribution of the mass around the body. Is the mass evenly distributed or is it not evenly distributed? What is the shape of the body and so on? So all these matter in rotational motion. They matter more in rotational motion, unlike in linear motion. So if you put all these together and you try to parallel this system with the previous graphs that I have shown, you'll come to the conclusion work in general will now be the integral of torque over angular displacement. Just like we had F dx for linear motion, now it will be T d theta. W equals to integral from 0 to theta of T d theta. And if we apply the laws of integration as we have done before, if torque is constant, you bring out the torque. Ultimately, we have work is equal to torque times angular displacement. So from all we've seen in the previous slide, and if we go back to the initial question, you see that all these A, B, C, D are actually correct. Force times distance is correct for a constant force. It's a correct definition of work. It's a correct mathematical definition of work in thermodynamics. Pressure times volume is also correct for constant pressure. Torque times angular displacement is also correct for constant torque. The integral of any of the first variables with respect to any of the second variable is also correct. In fact, that's a general definition of work, whether the force, pressure, and torque are constant or not. So D is also correct. So that leaves us with E as the answer, all of the above. So all of the above are correct mathematical definitions of work in thermodynamics. So we stop here for today. I believe it's clear to you how the concept of work is expressed in various forms mathematically in the field of thermodynamics. Now, these equations will be important as we do some simple but highly practical and relevant calculations and computations in heat engines as they apply to the broad subject of thermodynamics. So, thanks for listening. Until I come your way again, same time, next time. It is bye for now.